Welcome back, ladies and gentlemen. Today we are going to be discussing functions. Particularly, the things that we're going to be discussing about functions are how do we determine if a relation is a function or not, and how do we determine what the domain and range of a function is. So there's lots of different ways that we can look at these. Here we see the definition of a function to be a relation of a set of ordered pairs. Now, one of the things that I want to include in this definition is here the x numbers cannot, we'll put this all in capitals because it's important, repeat. The x numbers cannot repeat. Okay? That is the primary attribute that we generally think of as what makes a relation a function is that the x numbers cannot repeat. Now here what you see where it says a is equal to, and we have the curly brackets and a whole bunch of ordered pairs, we have one way that we can represent a function where we're just representing as a list of ordered pairs. Another way that we've seen how to list order or how to represent a function is something with a mapping diagram where we might have something that kind of looks like this and something that kind of looks like this, where we have 1, 2, 3, and then say -4, -5, -6, where each number of the input maps to some number on the output. Another way that we've seen functions represented is simply on a graph, where it might be a collection of just individual points on a graph where we can see it that way. Sometimes you'll see it more specifically as a type of function, like this would be a quadratic function. But those are different ways that we could represent it. And of course, the final way that we could represent a function is with an equation where we say y is equal to something. Okay? Now, generally speaking, the variables don't matter, but if we're keeping with the basics of y and x, then we're always going to say a function is y is equal to something x. Whatever type of function that could be, but that's how we represent it, where x is going to represent the input or the independent variable, and y is going to represent the output or the dependent variable. So one of the things that we want to talk about is how do we establish what is the domain and range of a function? How do we identify it? Now here they're giving you a pretty decent definition of how to identify the domain of a function, where it says the values of the first component of an ordered pair. And from what we see up on the top, they're kind of showing us, well, this is the domain. Generally speaking, more commonly, the way we would think of it is we're going to just say the domain are all of the x numbers. And consequently, the range would be all of the y numbers. That's all we really need to know as far as the domain and range. Now, identifying them sometimes can be a little bit challenging, particularly when it's on a graph. But as long as we can understand that the domain is made up of x numbers, input numbers, independent variable, whatever, then you're okay. Same thing with the range. As long as you know that the range comes from the y numbers, the output, the dependent variables, then you should be okay. So let's move on. Here, what we're going to be looking at is just how do we identify the domain and range of a function. So here we have 3 tables, and because the x numbers are the domain, then all we have to do is just list the x numbers that we see in the table, and that will tell us what the domain is. And consequently, the range would be all of the values in the y column. Now, if you notice, if something repeats itself, you don't have to write it twice. So for instance, in the last column here on the right, you see the 7 in the range column or in the y column is repeating itself, so we don't have to write it twice. We only write the things down once. So if a number repeats, we don't have to write it twice. So here, let's get a little bit more information up on the screen here so we can kind of talk about it a little bit more clearly. Here, again, a function is, well, this is what I wrote down at the beginning of the presentation. A function is a relation where it relates to a y value. But the thing is, the x numbers can't repeat. So as you see in the column, or in the table on the left, none of the x numbers repeat, so we would say that this relation is a function. Here, then the one to the next, or to the right of it, the 1 repeats itself here and here in the table. So because the x numbers repeat themselves, we would say that relation is not a function. And same thing with this last one here. None of the x numbers repeat, so that is a function. So this is one way that we can establish, is a relation a function or not, just to see, do the x numbers repeat? If they do, it's not a function. Okay, moving on. Pardon me. Here we're looking to see one of the ways that we can represent a function is in the form of an equation, which is a perfectly fine, perfectly valid way of doing it. Here we see y is equal to 2x minus 3. We would look at this as saying this would be a linear function, and you can see in the table that none of the x numbers repeat, and so we're okay. So we'd say yes, this is a function. Here we have y is equal to x squared and an associated table of values for it. Here, because the largest exponent is a 2, we would refer to this as something to be quadratic. And of course, because the x numbers don't repeat, it is a function. Now, positive 2 and negative 2, those aren't the same numbers. Same thing as positive 3 and negative 3. Those are not the same numbers. It's okay to have the same number of opposite signs because they're really not the same thing. Absolute value-wise, yes. So here we have an equation that says x is equal to y squared and an associated table of values. Now there's two things that kind of point this out to you, saying why this is not a function. First of all, the y numbers, the x numbers here, those are repeating. This set of x numbers here is repeating, and that is a clear giveaway. But how can I tell just by looking at the equation itself? What about this tells me that this is not a function? What tells me that this equation is not a function is because we're saying x is equal to something squared. That's kind of contradictory. That's the opposite of what we would see for the quadratic equation, where it says y is equal to something squared. The only way that we can tell if something is a function by the equation is it must say y is equal to x something. Okay, whatever we're doing to that x, the y must be just the y by itself. That's one of the primary ways. Now, that's not the only thing that we're going to be looking at to see if something is a function or not, but that is a clear tell if something is not a function. Okay, now we're going to look at graphs. Back in Algebra 1, you've talked about the vertical line test, where you took like your pencil or maybe a piece of spaghetti or just something, and you would kind of go across the graph from side to side, and you'd see, does the line touch the graph at more than one point? And if it did, we would say, well, it's not a function because that's an indication that the x values are repeating. So here, this little graph that we see here, maybe that is some kind of a polynomial graph. Then we can say, well, if we took the vertical line across there, we'd say, no, it doesn't touch any more than one place. And so we would say it's a function. Here we have an ellipse, and if we were to take a vertical line and go across it, you'd see very clearly, oh no, look, it's touching it more than one place. So that fails the vertical line test. So ellipses, circles, things like that, those are not functions. Now here, I definitely encourage you to copy these down, but these graphs that we're going to see are just the graphs of the equations that we saw earlier, so you can see why they are a good function. So if we were to plot those points and connect the dots, we would have a line. That's why we call it a linear function. and it would pass the vertical line test. The next one that we saw was here, the quadratic one, which again, if we plot those points, we would have a parabola, and none of the, now as it goes up on either side, it is going to look like it becomes steeper and steeper and steeper at some point, but the x numbers still don't repeat, so this is a good function. Okay, and the last one here, this is the one, this is another way why we can tell, because it doesn't say y is equal to something, if we were to plot the points for this one, we would have something that looks like this. It looks like a parabola turned on its side, and that's really exactly what it's called. It's called a sideways parabola. And you can see very quickly that that will fail the vertical line test. So just another reason to back up why we want to look at the equation to say y is equal to something and not x is equal to something y squared or anything like that. Now here is one of the things that we're going to be taking a look at. This is one of the things that students do have a tendency to struggle with when we're talking about domain and range of a function, particularly as a graph. Now we are going to have a tendency to use interval notation. Remember, interval notation is either going to use brackets or parentheses to show if it is included or not included. Remember, these are included. The parentheses are not included. I don't know what I'm thinking here. Not included. Cannot spell today. Not included. And those are going to be associated with a couple of things. The brackets, of course, are like greater than and equal to, but they are also solid dots, whereas the not included stuff is an inequality, is just a greater than, and on a graph we would associate it with an open circle, something like that. So looking at this one here, I'm going to go ahead and go through the presentation, and then I'm going to add some things to it just so that we can see more than one. Okay, well, what we're looking at for first is just the domain. Now, the domain is the list of the x numbers. So as you can see, we're kind of these vertical lines, these dotted vertical lines that you see here, all we're caring about is what is the x value from one point to the other. And that's why we're kind of drawing that line there. That's all we care about for the domain. So here, because the number furthest to the left has that solid dot, we'll use the bracket. And the number all the way to the right has a solid dot, so again, we use a bracket. And the number to the left, -3, the number to the right, +4. So that is the domain of this particular function. Now, what would the range be? We'll kind of do the range the same way, but in this case, range goes from top to bottom for the y-axis. Now, we always start with the smallest number first. So in this case, we start with the number that's at the bottom rather than to the left. So if we look at the number that's at the bottom, and we compare it to the number that's up at the top, we're going to go from a -4 on the y-axis up to a +2 on the y-axis. And both of the numbers are included because of the dots. So that's why we use the brackets here. In between the 4 and the 2. Now, this is not like a solution or anything like that, what we use interval notation for. We're simply saying that the domain is contained between the numbers -3 and +4. The range is contained between the numbers -4 and a +2. And that's really all we're kind of talking about. So I want to back this up just a little bit. So we can, I'm going to just add some things on here. I know that other one is on there, but let's go ahead and just add something else to it. And I'm going to say, let's put a circle here, and let's put a closed dot, let's say right here. And our function is going to do one of these things. I don't care what kind of function it is. Maybe it's a polynomial or something, but that's not what I'm really looking at. Okay, so the domain, okay, the number all the way from the left to the right, this is going to be the domain. So here at this one, I have the open circles. So that says I'm going to use the parenthesis to start that one. okay? And we are at 5 spaces. We're at -5 on the x-axis when we do that. Now, if we come all the way over here, this is 1, 2, 3, 4, 5, 6. This is at a +6, and it's included, so we use bracket. And we'll kind of look at the same thing with the range. Let me change colors here so we don't confuse what we're talking about. So the range kind of goes from here, and I missed it just a little bit. Let's just say it's going to hit this whole number right here. So the range is right here. So we start again with the smallest number. Now, there's no dot or anything showing that it's not included. It's a solid kind of thing, not a dotted curve or anything like that. So that tells me that it is included. And that goes down to a -2. And it goes all the way up to a 1, 2, 3, 4 on the y-axis. And because that circle is there at the 4, that tells me that it's not included. So we would show that the range is along the interval from -2 to a +4, not included, on the y-axis. Okay? So there's one extra example. Let's go ahead and fast forward just a bit to see where our next example gives us. Here, find the domain and the range of this particular graph. This is an absolute value function that we would see if we had an equation for it. You would see the absolute value symbol contained within it somewhere. And again, we're just kind of looking to see where does it stop on the x-axis. Now, if you notice, this one doesn't have a closed dot or an open circle. This has arrows on it. Those arrows indicate that it's continuous. Because it's continuous to the left and to the right, we would say the domain is all real numbers from -infinity to +infinity. So now let's take a look at the range. Okay, range again. Now in this case, the range isn't going to use all the real numbers. You can see it stops going down and starts going up to create that V shape at some point. So it stops going down at a -2. Now I know I'm going to use the bracket here at the -2 because the graph itself is a solid line. It's not like dotted or anything. So that tells me that the -2 is actually going to be used. But it goes up forever to +infinity, so it doesn't really stop. So that's why we can't actually include the number infinity. So that's why we include the parentheses on that one. Now I'm going to back this up just a bit so that way I can add a second graph to what we're going to be looking at here, just so I can give you a couple of different examples to look at, not just one. So now let's just add something here. Pardon me. Let's go right here, and let's give you something quadratic looking that way. Oh, let me clean that up just a little bit because I'm not thinking too clearly about where I want it to stop. All right, let's start again right here. So let's go right there and then turn around and come back. Okay, so something quadratic, and let's see how it goes. So the domain. The domain is all of the x numbers that are included. So from here, this is kind of where we start on the left, and the arrow indicates that it's continuous to the right. So here we're at 1, 2, 3, 4, 5 negative, and the open circle says to use a parenthesis. It's continuous going to the right on the x-axis, so that would be towards +infinity. Now let's take a look at the range. Okay, the range, the biggest y number that gets used is right here. And it goes down forever. So the range is going to be, again, we start with the smallest number, and -infinity is actually a really, really small number. So I start from the bottom and I work my way up. So from -infinity, I'm going to go up to, what is this number? 1, 2, 3, 4, up to a +5. And in this case, it is included because I have that solid line. So that's how I would write the range for the function that I added to the graph. So now let's move on just a bit because we're almost done talking with the stuff that we need. And I think that's it, actually, because the next stuff is getting into function notation, which we're not going to talk about just yet. So those are the main characteristics that we need to know for our functions. How do we identify a function as a set of numbers, as a graph, as an equation, and how do we identify the domain and range from either of those things? And that's going to do it for us for today. So thanks for watching, and I'll see you in class soon.